Qualcomm stands for quality communications. So we really want to connect everyone, everything, anytime you want, wherever you are.
I get to be one of the first people that get my hands on a brand new technology that's potentially going to be used by millions of people several years down the road. So that is probably the most exciting thing about my work.
In the last, I would say, 10 years, our mission has expanded quite a bit more beyond just connectivity. It's now also about the intelligence. So can you bring intelligence to your life?
The mission of Qualcomm, that's a broad question to answer, but I guess one of our key missions is to make sure that we are always innovating to wireless communications technologies, right? We're not necessarily just trying to, create a technology and sell it for our own interest, but we're also trying to shape this space.
The interesting challenge here is we are consistently improving the capabilities that we are bringing. From a G to G, the focus was initially on the device, now we're going to the network, and in a 6G, we're looking at this from a holistic piece, where we're not only minimizing the energy at the device, but also at the RAN, but also in the compute platforms, in data centers, in an end-to-end fashion, and hopefully able to offer new services that are actually more sustainable to the users.
A lot of cellular communication happened 2 gigahertz, 1 gigahertz, 2 gigahertz. That was 1G, 2G, 3G. And then since 4G, 5G, we have now expanded it vastly to tens of gigahertz. For 6G, probably the most important part is what we call the upper midband. That's between 7 and 16 gigahertz, I'll say. So that's where the new wide area cellular system is going to happen. But since we're a lot more than cellular, all the other frequency ranges matter too. If you want to, for example, talk to Internet of Things, a sensor, low power devices, it's very likely the communication will happen around 900 megahertz. And because the radio propagation property is much better at lower frequency, and the required bandwidth is not that much. On the other hand, if you are going to have some high-speed point-to-point link, we're investigating sub-terahertz.
Maybe a decade ago, nobody had smartphones that they were using on a day-to-day basis that would download, upload videos, use the chat applications, or even browse the web with their phone. So as we go towards next generation technologies, the demand for data is increasing exponentially. Probably the greatest challenge about the radio frequency spectrum is the spectrum crunch, because especially for the sub-7 gigahertz spectrum, that spectrum is heavily utilized by mobile broadband communications, TV broadcasting, and even for some satellite communications. So when it's that heavily utilized, it means that there is more interference across different users and the service quality degrades naturally.
In many senses, the term radio frequency interference, or RFI, depends on who's receiving the signal, right? So to a radio's telescope, a television broadcast is RFI, right? That is interference because it's not coming from the source. But to someone who's trying to receive that TV station, that's actually a signal, and it's a valid signal. What radio frequency interference looks like to a radio astronomer is you see a signal that's at a fairly high level that's in a part of the spectrum where you want to observe.
So what we're seeing is just a normal ground clutter pattern around the radar itself during the radar locations here. And here we have this interference spike that's persistent to the northeast of the radar, and you get a little bit to the east as well. And then here in our Texas example, we have this constant interference along this radial. So this is not what a radar operator would expect to see on their radar screen.
We've already seen issues that continue to grow because of the packing of the spectrum. And with time, we only expect that to increase. So we will constantly need to innovate, not only working better with partners, including other federal agencies to address spectrum issues, but looking at technology that can be used to improve interference issues.
If you are a commercial entity, you're supposed to have a license from FCC, the Federal Communication Commission. If you're a government entity, you have an assignment from the NTIA. FCC reports to Congress. NTIA reports to the President, the White House. Either way, this is actually documented in those two agencies who was actually allowed to operate, a license to operate on that frequency.
It's a determination made by policymakers on what is the most important use of the finite resource that is spectrum and the value that spectrum provides. The U.S. As a whole is working on strategies on the best use of spectrum, what we would term as the National Spectrum Strategy.
Clearly, there are a lot of business consideration as well. So it's beyond establishing a link, that's good, but you do need to think of what's the overall utility. Is the utility function a single link, capacity or signal to noise ratio, or actually the utility function is the fairness?
As we go from one technology to another, we're improving the technology and bringing capabilities that require frequency spectrum. At the same time, the resources that we are using are limited. As we come up with innovative ways to actually use these limited resources, we still have to be able to deliver performance, right? The end user expects some type of user experience, and we don't want to compromise on that. We want to deliver well. And also, when we give them that user experience, we want it to be cost effective for them.
It becomes clearer and clearer that we need to innovate in specific technologies that will help us manage, access to limited portions of spectrum, better management techniques for using limited spectrum. So that's actually a lot of what our engineers focus on.